Have you ever looked at a perfectly clear, high-resolution digital photograph and felt that something was missing? That for all its crystalline precision, it lacks the warmth, the unpredictable soul of reality? That's because every piece of technology you own, the smartphone in your hand, the screen you're watching this on, is built on a single, colossal assumption: that the universe, in all its messy, chaotic glory, can be perfectly translated into a language of zeros and ones. But what if that's not just an assumption, but a limitation? What if the very noise and imperfection we spent a century trying to eliminate is not a bug, but the secret ingredient to the next leap in creation? Today, we're going on a journey to the heart of chaos, to uncover a forgotten dream that's being reborn. A dream that suggests the future of intelligence isn't about perfection, but about embracing the beautiful, unpredictable static of existence itself. For the better part of a century, our world has been on a relentless quest for digital perfection. We live in an age that worships at the altar of binary logic. In this church of computation, everything must be absolute. A bit is either a 0 or a 1. A statement is either true or false. A transistor is either on or off. This philosophy has built our modern world, from the flawless architecture of a microprocessor to the rigid syntax of a line of code. We have engineered our digital universe to be clean, logical, and utterly predictable. We've built firewalls to keep out the unexpected, error correction codes to smooth over the glitches, and hermetically sealed data centers to protect our machines from the messy randomness of the physical world. We have, in essence, tried to build a digital heaven, a realm of pure order, shielded from the chaotic nature of reality. But step outside this digital cathedral, and you find a universe that not only tolerates imperfection, but thrives on it. Nature, the ultimate engineer, has never worked in absolutes. Think about the very essence of life: DNA. The process of evolution is driven by random mutations, errors in the code, so to speak. Most of these glitches are harmless or even detrimental, but every now and then, a mistake leads to a stronger, faster, or more resilient organism. The glorious diversity of life on Earth is not the product of a flawless blueprint. It's the result of billions of years of beautiful, chaotic, and unpredictable errors. Consider the human brain, the most complex computational device we know. It is not a perfect, silent processor. Your neurons constantly misfire. There is a persistent, low-level electrical noise crackling through your neural pathways. Yet, from this noisy, seemingly imperfect system, emerges consciousness, creativity, and the ability to dream. A painter doesn't create a masterpiece by placing every brushstroke with machine-like precision. It's the subtle, unintended variations, the slight tremor of the hand, the accidental smudge of color, that give the work its depth, its emotion, its humanity. A musician who plays every note perfectly on time, with flawless intonation, can sound sterile and robotic. It's the slight deviations, the tiny imperfections in timing and pitch, that we call feel or soul. Even the cosmos itself is a testament to the creative power of chaos. Stars aren't born from perfect uniformity. They coalesce from turbulent, uneven clouds of gas and dust. They don't die quietly. They explode in brilliant, cataclysmic supernovae, scattering the elements necessary for life across the galaxy. Chaos, it seems, isn't the enemy of creation. It is the engine. It's the raw, untamed energy from which order, complexity, and beauty emerge. Our digital world, in its pursuit of pristine logic, has walled itself off from this fundamental truth. We have built machines that are incredibly powerful, but also rigid and fragile. And now, as we try to teach these machines to be truly intelligent, to be creative and adaptive like us, we are slamming headfirst into the limitations of our own religion of precision. This obsession with a flawless, predictable world isn't a modern invention. It's a dream that has captivated scientists and philosophers for centuries. In the early 19th century, at the peak of the Enlightenment, the French mathematician Pierre-Simon Laplace gave this dream its most famous icon. He imagined a vast intellect, an entity that would later be called Laplace's demon. This demon, he theorized, would know the precise location and momentum of every single atom in the universe at one specific moment. For such an intellect, armed with a perfect knowledge of the laws of physics, nothing would be uncertain. The future, just like the past, would be present before its eyes. The universe, in this view, was nothing more than a colossal clockwork mechanism. Every star, every planet, every grain of sand, every human thought was just a cog in a machine, its movement determined by the state of the cogs that came before it. If you could know the initial setup, you could predict the entire history of the cosmos, from the Big Bang to the final heat death, with absolute certainty. This dream of total predictability was intoxicating. It promised a universe stripped of all mystery, a reality that could be fully understood, and therefore fully controlled. There was no room for chance, no place for randomness. Everything happened for a reason that could be calculated. And it was this very dream that became the philosophical blueprint for the digital computer. The pioneers of computing, Charles Babbage, Alan Turing, John von Neumann, were, in a sense, trying to build their own miniature versions of Laplace's demon. A computer, at its core, is a deterministic machine. If you give it the same input and the same instructions, it will produce the exact same output every single time without fail. It is a closed system designed to execute a flawless chain of cause and effect. The entire edifice of modern software engineering is built on this foundation. Flawless input should lead to flawless output. We write code with the expectation that it will behave predictably. We build hardware with the goal of eliminating any source of error or uncertainty. We are trying to create a pocket universe where the clockwork dream holds true. For tasks that are inherently logical and mathematical, this approach has been spectacularly successful. It has allowed us to calculate missile trajectories, sequence genomes, and simulate complex systems with astonishing accuracy. But we are now asking our machines to do something more. We want them to understand the nuances of human language, to recognize the emotion in a face, to create art that moves us. We are asking our clockwork machines to comprehend a messy, probabilistic, and fundamentally unpredictable world. And the clockwork, for the first time, is beginning to groan under the strain. The ghost of Laplace's demon still haunts our technology, but its promise of ultimate certainty is revealing itself to be not just a dream, but a beautiful cage, limiting our vision of what computation can truly be. But while the Western world was chasing the ghost of a deterministic universe, a different kind of revolution was quietly taking shape in Russia. It was here that a brilliant mathematician named Andrei Markov began to look at the world not as a perfect clock, but as a series of interconnected possibilities. He dared to challenge the prevailing dream of certainty, and in doing so, gave chaos a structure. Markov was fascinated by things that seemed random, but not completely random. He had a hunch that even within the most chaotic systems, there were hidden patterns, an underlying grammar to the apparent disorder. To explore this, he famously turned to literature, specifically Alexander Pushkin's epic poem, Eugene Onegin. He meticulously went through the text, not for its literary merit, but for its statistical properties. He created a massive chart, cataloging which letters were most likely to follow other letters. He wasn't looking at the text as a whole, but as a chain of events, where the probability of the next letter appearing depended only on the letter that came immediately before it. What he discovered was groundbreaking. He found that the sequence of letters was not purely random, nor was it perfectly predetermined. It was somewhere in between. For example, in Russian, a vowel is far more likely to be followed by a consonant and a consonant by a vowel. The letter Q in English is almost guaranteed to be followed by a U. The probability of the next event was not independent of the past, but it wasn't dependent on the entire past either. It depended only on the present state. From this simple yet profound observation, the Markov chain was born. A Markov chain is a mathematical model that describes a sequence of events where the probability of moving to the next state depends only on the current state. Think about predicting the weather. A full deterministic model would require knowing the position and momentum of every single air molecule on the planet. An impossible task, worthy of Laplace's demon. But a Markov chain approach is much simpler and more practical. To predict if it will rain tomorrow, the most important piece of information is whether it is raining today. The weather yesterday or the day before matters, but far less. The present state, rainy or sunny, holds the most predictive power for the immediate future. In that moment, Markov fundamentally redefined our relationship with randomness. He showed that chaos wasn't just incomprehensible noise, it had rules, it had patterns. Randomness could be described with the precise language of mathematics and probability. He gave us a tool not to eliminate uncertainty, but to understand it, to quantify it, and to work with it. He demonstrated that you don't need to know everything about the past to make a reasonable prediction about the future. This was a radical departure from the clockwork universe. It was an admission that perfect prediction might be impossible, but that meaningful understanding was not. Markov didn't defeat randomness, he tamed it. He gave it a leash. He showed the world that within the heart of chaos, there was a hidden, structured logic. And in doing so, he laid the mathematical foundation that would, decades later, allow us to build technologies that could navigate and make sense of our messy, unpredictable world. The dream of perfect certainty was beginning to fade, replaced by the far more powerful and practical language of probability. For decades, Markov's idea remained something of a mathematical curiosity, a brilliant but niche concept known mostly to statisticians and theorists. But as the 20th century progressed, and our problems became more complex, the world began to realize the immense power hidden within his chains of probability. Structured randomness evolved from an abstract theory into one of the most versatile and indispensable tools in modern science and technology. You interact with Markov's legacy every single day, whether you know it or not. When you type on your smartphone, the predictive text algorithm that suggests the next word is essentially a sophisticated Markov chain. It has been trained on billions of sentences and has learned the probability of which word is most likely to follow your current one. It doesn't understand grammar in the human sense, but it understands the statistical relationship between words. When Netflix recommends a new show, it's not because it knows your taste in some deep, personal way. It's because its algorithm has built a massive Markov model of user behavior, calculating that people who watched show A and show B have a high probability of also wanting to watch show C. This idea has reshaped entire industries. In finance, traders use Markov models to predict stock market fluctuations, analyzing current trends to forecast the probability of a market moving up or down. In genetics, biologists use them to model the sequence of amino acids in a protein, understanding the hidden patterns within our own genetic code. And perhaps most famously, the original algorithm that powered Google's search engine, PageRank, was a giant Markov chain. It ranked the importance of a web page by simulating the behavior of a random web surfer, calculating the probability that this surfer, clicking on links at random, would eventually land on a particular page. In a very real sense, the entire internet was organized and made navigable through Markov's vision of structured randomness. But the moment when randomness truly proved its worth came during one of the most chaotic and high-stakes challenges in human history, the building of the atomic bomb during the Manhattan Project. The scientists at Los Alamos were faced with a problem that traditional, deterministic mathematics couldn't solve. They needed to understand how neutrons would behave within a critical mass of uranium. A single neutron, upon striking a uranium nucleus, could trigger a fission event, releasing more neutrons, which would then strike other nuclei, creating a chain reaction. The problem was that this process was fundamentally random. You could never predict the exact path a single neutron would take. It might be absorbed, it might escape the material, or it might cause a fission event. The number of variables, the angles, the energies, the distances, was simply too vast to calculate with any conventional equation. The dream of a clockwork calculation had run headfirst into the reality of quantum uncertainty. The project was at an impasse, and the fate of the war hung in the balance. It was in this moment of crisis that the world turned away from the pursuit of absolute certainty and learned to embrace the power of the probable. Trapped by this seemingly impossible problem of predicting neutron behavior, a brilliant Polish-American mathematician named Stanislaw Ulam had a moment of insight while playing a game of solitaire. He was trying to calculate the probability of winning a particular game, a problem with so many possible card combinations that it was practically incalculable. Frustrated, he had a thought. What if he didn't try to calculate it at all? What if he just played the game 100 times? Or 1,000, and counted how many times he won? The ratio of wins to total games would give him a pretty good statistical estimate of his chances. He realized this same principle could be applied to the neutron problem. You couldn't calculate the exact journey of one neutron, but what if you could simulate the average behavior of many neutrons? This was the conceptual breakthrough that led to the Monte Carlo method, a name coined by his colleague Nicholas Metropolis as a nod to the famous gambling casino in Monaco, the ultimate temple of chance. Ulam rushed to his colleague, the legendary polymath John von Neumann, one of the principal architects of both the atomic bomb and the modern computer. Von Neumann immediately grasped the profound significance of Ulam's idea. Together, they refined it into a powerful computational technique. The method was deceptively simple. Instead of solving a complex deterministic equation, you would model the problem as a game of chance, and then play that game over and over again on a computer. To simulate the neutron chain reaction, they would create a single virtual neutron and give it a starting position and direction. Then, using random numbers, they would decide what happened to it next. Does it travel 1 centimeter or 2? Does it collide with a uranium atom? If it does, is it absorbed or does it cause fission? At every step, the computer would essentially roll the dice to determine the outcome based on known probabilities. After simulating the entire life story of this one neutron, they would start over with a new one, and then another, and another, thousands upon thousands of times. Each individual simulation was random and unpredictable. But by running countless trials and averaging the results, a clear and incredibly accurate picture emerged. The chaos began to reveal a statistical truth. They could reliably predict what percentage of neutrons would cause fission, what percentage would escape, and whether the overall reaction would sustain itself and lead to an explosion. It was a stunning victory. By embracing randomness, they had solved a problem that was impossible for deterministic mathematics. They had found a way to make chaos predictable, not by eliminating it, but by sampling it enough times that its underlying order became visible. The Monte Carlo method was a revelation. It transformed randomness from a scientific nuisance into one of the most powerful and reliable tools of the modern age. Today, it's used everywhere. It helps engineers design safer cars by running thousands of virtual crash simulations. It allows meteorologists to create ensemble weather forecasts, running the same model with slightly different random starting conditions to see the range of possible outcomes. It's used in computer graphics to create incredibly realistic lighting and textures by simulating the random paths of millions of light rays. Stanislaw Ulam Desesmi a simple idea that you can understand an unpredictable system by sampling it had fundamentally changed our relationship with uncertainty. He and von Neumann had shown the world that sometimes the best way to find a single, reliable answer is to ask a million random questions. For most people, the success of the Monte Carlo method was the final word. It was a brilliant trick, a clever way to use deterministic computers to wrestle with the probabilistic nature of the universe. But for a mind like John von Neumann's, it was just the beginning. He saw something deeper in their success. He began to wonder if they were going about it all wrong. Why build a perfectly precise deterministic machine only to then feed it random numbers to simulate a random world? It was like building a perfectly sterile operating room and then opening all the windows to let the germs in. It was inefficient, indirect, and philosophically backward. This led von Neumann to a truly radical and visionary idea, one that was decades ahead of its time. He imagined a completely new kind of computer, a machine that didn't just use randomness as a tool, but was built from it at the most fundamental level. He envisioned a computer that didn't resist the inherent noise and chaos of the physical world, but actively embraced it and used it as a computational resource. This was the birth of the concept of stochastic computing. In a conventional computer, a number is represented by a fixed set of bits. The number 5, for example, is represented in binary as 101. It is a precise, static, and unchanging value. Von Neumann's idea was to represent numbers in a completely different way, as a stream of random bits flowing over time. In this system, the value of a number would be represented by the probability that any given bit in the stream is a 1. For example, the number 0.75 would be represented by a long stream of zeros and ones where, on average, 75% of the bits are ones. The number 0.5 would be a stream with an equal mix of zeros and ones. The number 0 would be all zeros, and 1 would be all ones. The implications of this were astounding. Basic mathematical operations suddenly became incredibly simple. To multiply two numbers, say 0.5 and 0.5, you wouldn't need a complex multiplication circuit. You would simply take their two random bit streams and pass them through a single basic logic gate, an AND gate. Since an AND gate only outputs a 1 if both of its inputs are 1, the resulting stream would have a probability of being 1 equal to 0.5, 0.5, which is 0.25. Multiplication, one of the more complex operations for a conventional computer, was reduced to the simplest possible hardware. This was computation by probability, order emerging directly from chaos. Von Neumann saw that such a machine would have incredible advantages. It would be highly resistant to errors. In a binary computer, if a single bit flips from a 0 to a 1 due to radiation or a hardware fault, it can completely corrupt a calculation, turning a small number into a massive one. But in a stochastic computer, a few flipped bits in a long stream would barely change the overall probability. The result would be slightly noisier, but still approximately correct. The machine would be gracefully degradable, not catastrophically fragile. It would also, in theory, be incredibly energy efficient, as the components required were far simpler than their deterministic counterparts. This was von Neumann's grand vision, a computer that worked like the brain, one that was noisy, probabilistic, and robust. A machine that didn't fight against the fundamental nature of physics, but instead made a pact with it. It was a departure not just from the engineering of the time, but from the entire philosophical tradition of Western science that stretched back to Laplace. He was proposing that we stop trying to build a perfect clock and instead learn to compute with the clouds. It was a beautiful, radical, and almost heretical idea. And for a brief moment in history, in a small lab in England, it seemed like this forgotten dream might actually come true. Inspired by von Neumann's paradigm-shifting vision, a team of bold engineers at the University of Manchester in the 1960s set out to build what he had only imagined. They embarked on a project to construct the world's first truly stochastic computer. They called it RASEL, which stood for Random Sequence Computing Element. This wasn't a machine that simulated randomness. It was a machine that was alive with it. RASEL was a strange and wonderful beast, a complete departure from the clean, orderly logic of its contemporaries. Instead of representing numbers with fixed binary digits, it used von Neumann's probabilistic bit streams. Its circuits were designed to perform calculations by manipulating these streams of chaos. The machine was, by its very nature, noisy. The results it produced were not single, precise answers, but statistical approximations that grew more accurate the longer you let the machine run, and the more random bits it processed. One of its most remarkable properties was its inherent resilience. The engineers discovered that RASEL could continue to function even when parts of it were damaged or failed. Because its calculations were distributed across a probabilistic system, the failure of a single component didn't cause a catastrophic crash. It just introduced a little more noise into the system. The final answer might become slightly less accurate, but the computer would keep on computing. It was, in a sense, self-healing. Like a biological organism that can sustain an injury and continue to live, RASEL had a robustness that its fragile, deterministic cousins could only dream of. For a moment, it seemed like the future of computing had arrived. Here was a machine that embraced the imperfection of the physical world, a computer that was tough, efficient, and philosophically aligned with the probabilistic nature of reality. But the brilliance of RASEL came with a crippling cost. The machine was agonizingly, painfully slow. The problem was that to get a reasonably accurate answer, Russell needed to process incredibly long streams of random bits. To represent a number with just 8 bits of precision, which is very low by modern standards, it would need to process a stream of 2 root 8, or 256 bits. To get 16 bits of precision, it would need over 65,000 bits. For the kind of accuracy required for serious scientific work, the streams would have to be astronomically long. While a conventional computer could perform a multiplication in a handful of clock cycles, Russell took an eternity to arrive at a comparable result. It was a tortoise in a world that was rapidly falling in love with the hare. At the same time, the world of conventional binary computing was exploding. Moore's law was in its infancy, and the power and speed of deterministic transistors were doubling every couple of years. The problems of fragility and error were being solved with brute force, cleaner manufacturing, better error correction codes, and sheer, breathtaking speed. The slow, probabilistic, and somewhat unstable nature of Russell couldn't compete. The industry had made its choice. It chose the path of precision, speed, and deterministic certainty. By the late 1970s, the dream of stochastic computing was all but dead. Research funding dried up. The projects were cancelled. The ideas of von Neumann and the strange, noisy machine from Manchester were relegated to a forgotten footnote in the history of computer science. It was shelved as a beautiful, brilliant impossibility, a fascinating dead end on the road to our digital future. The world had doubled down on the religion of precision, and for the next 40 years, it seemed like the right bet. But no path continues forever, and the cracks in the foundation of our perfect digital world were already beginning to form. For decades, the path of precision computing seemed limitless. Moore's law became a self-fulfilling prophecy, a relentless drumbeat of progress that gave us smaller, faster, and more powerful chips year after year. This exponential growth fueled the digital revolution, giving us everything from personal computers to the internet and smartphones. We built a world on the foundation of flawless binary logic, and it was a spectacular success. But in recent years, the drumbeat has begun to falter. The cracks are starting to show. The relentless shrinking of transistors is slamming into the hard limits of physics. As we approach the scale of individual atoms, quantum effects, the very randomness we tried so hard to eliminate, are beginning to interfere, making transistors leaky and unreliable. The energy required to power our ever-growing digital world is becoming unsustainable. The massive data centers that power our cloud services and AI models consume as much electricity as entire countries, and their appetite is only growing. The pursuit of ever greater precision is demanding an impossible price in both energy and complexity. This crisis has become most apparent in the field of artificial intelligence. We are trying to build machines that can think, learn, and create like a human brain. Yet, we are trying to do it on hardware that is fundamentally alien to the way biology works. The human brain performs its magic while consuming about 20 watts of power, less than a dim light bulb. By contrast, training a single large AI model, like GPT-3, can consume an amount of energy equivalent to driving a car to the moon and back. We are trying to simulate intelligence using a brute force approach, demanding an astronomical level of mathematical precision from our silicon chips to replicate something that nature accomplishes with noisy, low power, and imperfect components. It is in this moment of crisis, with the old path reaching its end, that we are forced to look for new ones. And sometimes, the new path is one that was abandoned long ago. Scientists and engineers, faced with the insurmountable challenges of conventional computing, began to rummage through the dusty archives of their field. And there, they found it. The lost idea of John von Neumann. The forgotten dream of a computer that doesn't fight against the noise of the universe, but embraces it. Suddenly, the weaknesses of stochastic computing started to look like strengths. Its slowness was a problem in an era of simple calculations, but for the complex probabilistic problems of modern AI, perhaps speed wasn't the only metric. Its inherent noise and inaccuracy, once seen as fatal flaws, now looked remarkably similar to the way a biological brain works. Perhaps the key to building an efficient, intelligent machine wasn't to demand perfect precision, but to give it up entirely. The forgotten dream was resurfacing. The idea that imperfection wasn't the enemy, that randomness wasn't a flaw to be corrected, but a resource to be harnessed, began to gain new currency. What if, after a 50-year detour down the road of digital perfection, the true path forward was the one we had abandoned? The world was finally ready to ask the question that von Neumann had posed decades earlier. What if we stopped trying to build a perfect machine and started building one that was beautifully, powerfully, and intelligently imperfect? In the world of technology, dominated by giants like Intel, Google, and Nvidia, it's often the small, audacious startups that dare to dream differently. As the limitations of conventional computing became a crisis for the AI industry, a new company emerged with a philosophy so radical it felt like a message from another timeline. This startup, aptly named Normal Computing, didn't just want to build a better chip. They wanted to resurrect von Neumann's forgotten concept and build a completely new kind of computer. Their core philosophy was a direct challenge to the entire history of digital engineering. For 70 years, the goal had been to fight physics. Engineers have gone to extraordinary lengths to create transistors that behave as perfect, identical, deterministic switches. They have built elaborate systems to suppress electrical noise, to shield chips from radiation, and to correct for the tiny, random fluctuations that are an inescapable part of our physical reality. Normal computing's philosophy was the polar opposite. Don't fight physics, use it. They looked at the electrical noise that every other company considered an enemy and saw it as a powerful, untapped resource. Instead of building transistors that are forced to be either perfectly on or perfectly off, they designed chips that allow their components to flicker, to exist in a state of managed unpredictability. Their hardware doesn't suppress the inherent randomness of electrons. It embraces it, it amplifies it, and it puts it to work. Their chips are not silent, orderly grids of logic. They are a living sea of probability. The constant, random fluctuation of the transistors creates a dynamic, ever-changing landscape of electrical potential. This isn't a bug. It's the central feature of the machine's operation. It is a physical embodiment of a stochastic system. They have created a piece of silicon that doesn't just simulate randomness with pseudo-random number generators. It directly taps into the true, chaotic noise of the universe and uses that energy to perform computation. In essence, they are building a computer that thinks in probabilities, not in certainties. It doesn't follow a rigid, pre-programmed set of instructions in a deterministic way. Instead, it explores a vast space of possibilities, guided by the very laws of thermodynamics and quantum mechanics. It is a machine that has closed the gap between the mathematical model and the physical reality. It is a computer built in nature's own image, noisy, messy, and alive with the hum of chaos. The dream of von Neumann was no longer just a theoretical concept. It was being etched into silicon. So, how does a machine built on randomness actually compute anything useful? The process is fundamentally different from the rigid, step-by-step logic of a conventional computer. It's less like solving a math equation and more like watching a natural process unfold. Imagine a complex problem as a vast, hilly landscape with many valleys. The solution to the problem is located at the lowest point in the entire landscape. A conventional computer tries to solve this by creating a perfect, detailed map of every single hill and valley, an incredibly time-consuming and energy-intensive process. It calculates its way to the bottom. Normal computing's processor works in a completely different way. Instead of mapping the landscape, it essentially drops thousands of tiny marbles all over it. These marbles are the computations, and their movement is guided by the random thermal noise of the chip itself. They jiggle and wander around the landscape, a process much like particles in a gas. Naturally, more marbles will begin to settle in the valleys, the areas of low energy. Over time, through this random, chaotic exploration, the vast majority of the marbles will find their way to the very lowest valley in the entire landscape. The computer doesn't calculate the answer in a traditional sense. It settles on it. It lets the physics of the system do the heavy lifting. The processor wanders through the vast space of possible solutions, gradually converging on the most probable, lowest energy state, which represents the optimal answer. It's not a piece of software solving a problem, it's the universe itself, embodied in a piece of silicon, computing its own most likely outcome. This approach is incredibly well suited for the types of problems that plague modern AI, such as optimization and sampling. These are tasks where finding a good enough answer quickly is often more important than finding a single, perfectly precise answer slowly. For generative AI, which creates new text, images, or sounds, this method is a natural fit. Instead of using immense computational power to deterministically calculate the single best next word or pixel, a stochastic processor can explore a whole probability distribution of good options, leading to more creative, varied, and less robotic outputs. It represents a profound shift in what it even means to compute. For a century, we have told our machines exactly what to do at every single step. We have been the architects of a deterministic process. With this new form of computing, we are becoming more like gardeners. We prepare the soil and plant the seed. That is, we define the problem landscape, but then we let nature take its course. We let the system grow and settle into its own solution, guided by the fundamental, creative chaos of the universe. At the heart of normal computing's machine lies a critical distinction that separates it from almost every other computer on the planet: the source of its randomness. Most of the random numbers used in conventional computing, from video games to cryptography, are not truly random at all. They are pseudo-random. A pseudo-random number generator is an algorithm, a deterministic piece of code. It starts with an initial value, called a seed, and then performs a series of complex mathematical operations to produce a sequence of numbers that appears random. The sequence looks unpredictable, and it passes many statistical tests for randomness. But it has a hidden, fatal flaw. It is ultimately a repeating pattern. If you know the algorithm and the initial seed, you can predict the entire sequence, and eventually, given a long enough run, the sequence will start over. It is a convincing imitation of chaos, but it is not the real thing. Normal computing's approach is to bypass this imitation entirely and tap directly into the source. Their chips are designed to harness thermal noise. This is the true, unpredictable randomness born from the very fabric of nature. It is the microscopic jiggling of atoms due to their thermal energy, the fundamental quantum uncertainty of electrons. This is the universe's own background static. Unlike a pseudo-random generator, it never repeats. It has no underlying pattern. It is not an algorithm. It is a physical phenomenon. By building their processors on this foundation, every stream of bits their computer generates is a raw, unedited sample of reality itself. When their machine computes, it is drawing its chaotic energy directly from the universe. This has both practical and philosophical implications. Practically, it means their machine has access to a source of infinite, high-quality randomness that is incredibly difficult for conventional machines to replicate. For applications in fields like secure communications, scientific simulation, and advanced AI, access to true randomness can be a game changer. Philosophically, it is even more profound. It represents a reunification of computation with the physical world. For decades, we have tried to create an abstract digital realm that is separate from and protected from the messiness of reality. This new approach tears down that wall. It suggests that the most powerful form of computation is not one that ignores the universe, but one that is in direct conversation with it. It is computation drawn from reality, to understand reality. The machine is no longer just a tool for calculation. It becomes an instrument for listening to the deep, chaotic, and creative hum of the cosmos. Normal computing's prototype, a tangible result of this radical philosophy, has proven that the concept works. They have successfully built a chip that powers generative AI models not through the rigid, brute force mathematics of deterministic logic, but through the elegant, efficient dance of stochastic physics. The machine can generate novel outputs, explore complex possibility spaces, and solve optimization problems in a way that is fundamentally different from its conventional counterparts. This achievement is more than just a clever engineering feat. It's a signpost pointing toward a dramatically different future for computing. It suggests a world where our machines are no longer defined by their pursuit of flawless precision. In this future, we may see specialized chips, or stochastic coprocessors, that work alongside our traditional CPUs and GPUs. The conventional chips would handle the tasks that require deterministic accuracy, like running an operating system or calculating a spreadsheet, while the stochastic chips would take on the messy, probabilistic workloads of AI, creative generation, and complex simulation. Imagine an AI artist powered by a stochastic chip. Instead of methodically calculating every pixel, it could explore a landscape of artistic possibilities, settling on compositions that are not just technically correct, but also surprising and novel. Imagine a drug discovery program that could sift through millions of potential molecular structures, not by testing them one by one, but by letting the problem space physically resolve to its most stable and effective configurations. Of course, this new kind of machine is not yet ready to replace the conventional chips in your laptop or phone. The technology is still in its infancy. It is less a universal solvent and more a specialized key, designed to unlock problems that have proven stubbornly difficult for our current methods. It cannot yet match the raw speed and precision of a modern CPU for many tasks, but that isn't the point. A bird can't carry as much cargo as a freight train, but it can fly. This machine can do something that our digital freight trains cannot. It can navigate the world of uncertainty and probability with a native fluency. Normal computing's prototype is a proof of concept, a demonstration that the forgotten dream of von Neumann is not an impossibility. It shows that there is more than one way to build an intelligent machine. We don't have to keep building ever larger, ever more power-hungry monuments to precision. We can instead build machines that are smaller, more efficient, and more aligned with the fundamental principles of nature. They are no longer trying to imitate perfection. They are beginning to embody the creative, chaotic, and beautiful logic of the universe itself. This journey, from the clockwork dream of Laplace to the noisy silicon of normal computing, is more than just a story of technological evolution. It represents a profound philosophical shift in how we view the universe and our place within it. It's a story about our changing relationship with two fundamental concepts: randomness and perfection. For centuries, guided by the light of the Enlightenment, we saw randomness as an enemy. It was ignorance, disorder, a flaw in our understanding. The ultimate goal of science was to eliminate it, to peel back the layers of chance until the perfect deterministic machinery of the cosmos was revealed. From Markov's structured patterns to the Monte Carlo method's statistical truths, the story of the last century of science has been one of slowly, grudgingly, making peace with this flaw. We learned that while we might not be able to defeat randomness, we could at least understand it, manage it, and use it to our advantage. This new wave of stochastic computing takes the final step in this philosophical journey. It proposes that randomness isn't a flaw at all. It is the foundation. It is the raw material of creation, the engine of computation, the very language the universe speaks. The universe, this new paradigm suggests, does not compute with the absolute certainty of a 1 or a 0. It computes with the infinite possibility of maybe. It explores, it weighs probabilities, it settles into states of likelihood. What we have been building with our binary computers is a clever but artificial imitation of this process. Stochastic computing is an attempt to compute with reality itself. This forces us to reevaluate our obsession with perfection. We have long equated perfection with strength, with reliability, with intelligence. We build flawless machines because we believe they are superior. But nature teaches us a different lesson. A perfectly pure crystal is incredibly strong, but it is also brittle. A single, well-placed strike can shatter it. A slightly impure alloy, however, is often more resilient, able to bend and absorb shock without breaking. Perfection is fragile. The pursuit of it often leads to systems that are powerful, but unable to adapt to the unexpected. The universe isn't a perfect crystal. It's a messy, resilient, and ever-evolving alloy. And perhaps the machines we build to understand this universe should reflect that. The shift from deterministic to stochastic computing is an act of intellectual humility. It's an admission that our models of the world will never be perfect, and an acceptance that the most powerful way to engage with a probabilistic reality is with tools that speak its native language. As we stand on the cusp of this new computational era, we are forced to ask a deeper question. What is intelligence? For decades, we have implicitly defined it through the lens of our own technology. We thought of intelligence as a form of flawless, logical calculation. We built chess machines that could out-calculate any grandmaster and called them intelligent. We built AIs that could process vast amounts of data with perfect accuracy and assumed they were on the path to consciousness. But what if intelligence isn't about logic at all? What if, at its core, it is something much closer to what is happening inside these new stochastic chips? Perhaps intelligence is simply structured noise that is learning to understand itself. Think of your own mind. When you have a creative insight, does it arrive as the result of a neat, logical deduction? Or does it bubble up from a chaotic soup of half-formed thoughts, memories, and emotions? Consciousness itself feels less like a deterministic algorithm and more like a wave, a probability distribution that momentarily collapses into a single, coherent thought before dissolving back into the sea of possibility. Maybe our attempts to build artificial intelligence have been hampered by a fundamentally flawed definition. Maybe true progress doesn't lie in building ever more perfect thinking machines, but in embracing the beautiful, essential disorder of reality. We may find that the key to creating a truly intelligent, adaptive, and creative artificial mind is to give it the one thing we have tried so hard to deny our machines: the freedom to be imperfect. The lesson here extends far beyond the realm of silicon chips and into our own lives. We often strive for a kind of Laplacian perfection in our own affairs. We create rigid plans, we try to control every variable, and we see unexpected events, randomness, as a failure or an interruption. We fear the noise, but this story teaches us a different way. It teaches us that the noise is where the music is. The unexpected mutation is what drives evolution. The random encounter is what leads to love. The misstep is what leads to a new discovery. Perfection is a static, sterile end state. It is fragile. But the noise, the chaos, the beautiful imperfection that endures, it is the source of all resilience, all creativity, and all life. Within that beautiful disorder, the next generation of intelligence, both artificial and human, is already awakening. So, I leave you with a question to ponder. Where in your own life have you been fighting against the noise? Where have you been demanding perfection, when embracing a little bit of chaos might lead to something far more creative and resilient? I'd love to hear your thoughts in the comments below. Thank you so much for joining me on this journey today. I wish you all the best of health and a mind open to the beautiful possibilities of imperfection. And if you enjoyed this exploration into the heart of chaos, please don't forget to like, share, and subscribe to the channel for more stories that challenge the way we see the world.